Good evening, everyone. Thank you for the kind introduction, Martin, and some of them were not true, but I will take the credit. Before we begin, we want to observe 30 seconds of silence in honor of the lives lost in that two tragic earthquakes. So I am going to run a video, and some of the images in this video may be disturbing to some of you. Okay, thank you. That's the outline of a talk, and we are going to start by giving some background on the tectonic setting, faults and earthquakes, but to put some perspective about these two major earthquakes which occurred on February 6, 2023. And we'll give us a summary of that one, followed by a summary of our reconnaissance trip. Then I will give you an overview of these two major earthquakes and their impacts on the people and economy and the infrastructure, followed by the focus of our talk today, which is geoseismic impacts. And finally, we will end with a summary, lesson learned, and also we will draw some parallels with the conditions here in Southwestern BC. And this slide shows the Turkey and the two ruptures which occurred due to these two major earthquakes. The first one is the 7.8 magnitude earthquake, and the other one is the 7.5 magnitude earthquake, which occurred 9 hours after the other, which is kind of unusual. And this figure shows the tectonic setting of the Turkey, the major plates and the two major fault system, and one of them is the North Anatolian fault, and the other one is the East Anatolian fault at the south. And Turkey is one of the most seismically active regions in the world, and the figure at the bottom, it shows that the Arabian plate is converging into the Eurasian plate, and this causing this Anatolian block where the most of the Turkey is located westward direction, motion in the west direction. And this westward motion is accommodated by the North Anatolian fault at the north, which is about 1,500 kilometer long right lateral strike slip fault, and the at the south by this East Anatolian fault, which is a left lateral strike slip fault. And these two major earthquakes occurred on this East Anatolian fault system. And the North Anatolian fault has been quite active, and since 1900 there were many earthquakes, 11 earthquakes with magnitude greater than M7. And the notable earthquakes are 1930s 7.8 magnitude Erzincan earthquake that cost about 32,000 lives, and the 1999 7.6 magnitude Izmit earthquake that killed about 17,000 people. And if you look at the figure at the left-hand side, you can see the earthquakes with magnitude greater than 7, and most of them are on that North Anatolian fault. But if you look at the East Anatolian fault at the south, and there were no M7 earthquake until this February 6. And in this East Anatolian fault, there have been several earthquakes with the magnitude 6 and 6.9. And a notable one is this 6-point earthquake which occurred in 2020. Prior to that, February 6, 2023 earthquakes. And this slide shows the first figure shows the faults. The second figure shows that how active this Turkey is. It shows these earthquakes with magnitude greater than 7. And the figure at the bottom, which shows the seismic hazard map for the Turkey. And what is shown there is the 475-year return period earthquake peak ground acceleration, or PGA. And the red color shows the PGA with 0.5 G or greater, and the yellow shows between 0.1 and 0.2 G. And you can see that the high ground motions are around these two major fault systems, the North Anatolian Fault and the East Anatolian Fault and the South. And the region at the west also is quite active due to some extensional structures there. So let's look at these two major earthquakes which occurred on February. The first event occurred early morning 4:17. It's called Pasasik earthquake, and the magnitude is 7.8 according to USGS and 7.7 according to AFAD, which is the Turkish agency. And it caused more than 300 kilometer rupture, and surface displacement exceeded 4 meters. And there was a magnitude 6-point earthquake 10 minutes after that one. And 9 hours later, at 1:24 p.m., this Elbistan earthquake occurred, and that is a 7.5 magnitude earthquake, and it ruptured about 150 kilometers, and the surface displacement exceeded 6 meters. And one of the key thing about this particular earthquake is there was more than 11,000 earthquakes within 200 kilometers by March 1st, and 400 of them were had a magnitude greater than 5. You can see how many aftershocks have occurred. And this slide shows the two ruptures and the location of these two earthquakes, the 7 and 7.5 earthquakes. And the rupture extended to more than 300 kilometers and affected about 11 provinces with some 15 million people. So it's a very large area which was affected by that one, and the entire 300 kilometer, more than 300 kilometer rupture due to that first earthquake. And the second earthquake up in north of that one, that ruptured about 140 kilometers. And these figures are from the USGS. It shows that how that rupture occurred. Let me see, I can run this video. It shows that the first earthquake occurred on the Nali fault, then it jumped into that main fault, then propagated both in the east and west directions to more than 300 kilometers. And the second rupture is due to that second earthquake, and which occurred on the Sugu-Kadak fault and ruptured about 140 kilometers. The figure on the right-hand side shows the distribution of the aftershocks, and you can see that it extended over the entire ruptured area. And the bottom figure shows this magnitude versus time over a period of 15 days. And some information about this reconnaissance trip. Martin talked briefly about it, and we went to the earthquake 3 months after these major earthquakes in May. The Canadian Association of Earthquake Engineering put together a 12-member team, and Tyler and myself were the geotechs in the team. Martin was the geologist, and the rest of the members were structural engineers. And we went there our objective was to observe impact, collect perishable data, identify gaps in research and practice, and share the lessons and the data with the community. I will show you our travel route. We went to the Istanbul, which is the capital of the Turkey. Then we first flew to Ankara and met some academics and government officials there, and they shared some information with us prior to our reconnaissance trip based on their reconnaissance, which was quite useful, and also they gave some perspective about why there was so much damage to the buildings, which we will highlight later. Then we flew to Adana and spent 3 days there and traveled to this south area in the Hatay province. Then we drove to the Gaziantep, or it's called Antep, and we spent 4 more days there. And we traveled more than 450 kilometers and visited most of the affected areas in that region. And let's look at the impact of earthquake on population and the infrastructure. And these two earthquakes affected about 15 million people in 11 provinces, extending over 400 kilometers. And more than 60,000 people lost their lives and 120,000 injured. And when we visited after 3 months, people were still living in temporary shelters and tents, and they were lining up for rations. The situation was that bad, but the general public started to move on and getting on with their lives. And these earthquakes cost $104 billion, which is about 13% of the 2021 GDP of the Turkey. And one of the things we want to talk about is what did not perform well and what performed well. When we talk about earthquakes, we always concentrate on the failures and damages, and we learn from the failures and improve their practices. But at the same time, we also want to learn from what performed well. And there were lots of examples from these two earthquakes, despite this, loss of life and major failures. So there were widespread damage to the buildings across the region, and the damage to the buildings were much greater than the other infrastructure. And the damage to the buildings was mostly responsible for the loss of lives and injuries. And there were damage to the port structures near the waterfronts, and there were flooding due to the subsidence in those regions. And this slide shows that if you consider the total number of buildings in the affected region, only 14% of them heavily damaged, collapsed, or required urgent demolition. But at the same time, the 50% of the buildings were undamaged. And it's not that, we have been to, many areas. We traveled over 400 kilometers, and we haven't come across an area where the entire building stock was wiped out by the earthquake. And one example of that one is on the right-hand side. You can see the picture before and after. And the after picture shows, of course, there were several buildings which collapsed, but still there were several buildings which were still standing up. And this slide shows the damage to buildings in and around the rupture extended to that 300 kilometer, and the red color dot shows the collapsed building, and the blue color shows the slightly damaged buildings. And you can see that this damage, of course, concentrate on the cities close to that rupture. And you can see more red dots at the south, which is close to the coast, and where we have these deep sediments, and where we probably had much higher ground amplification and liquefaction. And let's look at what performed well. If you look at the impact on bridges in the affected region, there were 1,000 bridges. but only 15 were affected, and half of that one was restored within a day. And if you look at the tunnels, there was only one tunnel which was built in 1940 was severely damaged, and the other tunnels actually performed well. And if you look at the dams, there were 140 dams in the affected region, and 100 of them were earth and rock-filled dams. And there were also concrete-faced and membrane-faced dams, and 15 of them, and RCC dam and arch and gravity dams as well. And these dams were used for water supply, irrigation, flood control, and hydropower. And the dams were located very close to the rupture surface and within 10 to 20 kilometers and experienced 0.5 G. But out of that 140 dams, only 17 dams experienced minor to major deformations. And there were some cracks on the dam crust, and so in a few dams there were giant cracks, but none of the dams failed, none of them breached, resulting in the uncontrolled release of the reservoir. So that the performance of the dams, the performance of the bridges and tunnels were remarkable. Actually, it helped to in the rescue and the recovery operation, and bring these lives back to normal quicker than in other regions. And when we looked at these dams further, the embankment dams suffered the most damage compared to the concrete CRFD and RCC dams. And when we visited this dam site, there were significant cracks. We of course visited the dams which are damaged due to the earthquake. There were significant cracks. Still, they were not repaired even after the 3 months in some of the dams. But if you look at the spillways and other structures, they were not damaged. Even one of the dam, which is Sultan Suyu Dam, which was severely damaged, but still the spillway and the low-level outlet were operating. And the most of the cracks were longitudinal cracks on the crust of the dam, and we haven't seen any transverse cracks or any downstream seepage or anything like that one. But in a few dams, there were transverse cracks too. And this slide showed the major cracks were the 1.5 meter, but in 1 or 2 dams, it was more than that one, around 3 meters. So, the impact would have been, much worse if not for the good performance of this transportation and other infrastructure like the dams. So, this slide shows some of the post-earthquake repairs, and Tyler will go into more detail to some of them. And what Turkey did is, even for the few bridges which were damaged, they came up with some somewhat unique quick fixes which may not be acceptable in Canada, but it worked, and they let the traffic go on them. And when it comes to the dams, they simply fill up the cracks with the sand and bentonite, and raise the dam and pave the dam. The picture in the middle picture at the bottom shows that one, and one of the dam. If it's a transmission line failure, they simply realign that one. So they were they came up with some quick fixes in that country, and it worked. When we went 3 months after the earthquakes, like I mentioned, people were still living in tents and shelters, but people started to move on, right? And we were amazed to see their resilience and also their hospitality. When we were traveling around, they invited us for, tea, and they provided food despite living in tents, right? And the photo at the bottom right corner, which shows a group of happy kids. Actually, they showed us the way to the giant landslide because we went there and got lost. So I'm going to invite Tyler. He's going to talk about the most important thing of the presentation today, which is the geoseismic impacts.
Thank you, Thava. So as Thava mentioned, there is extensive geoseismic impacts. They went from ground motion amplification, ground rupture, seismic soil structure interaction. There's extensive liquefaction, which manifested in both differential as well as uniform settlements, also lateral spreading, seismic slope stability issues, and also, as Thava mentioned, the effects of this on infrastructure were immense. But before we get into that, I think it's good to take a step back and talk a little bit about Turkey's seismic design codes. So their first seismic design code, very similar to Canada, was in the 1940s. So that was when, it was immediately following the 1939 Özerken earthquake, and so there was sort of seismic loading independent of location. And then through a series of different code changes, they got to their most recent design code, which was published in 2019. The other large design code update that's sort of important to keep in mind is around 2000, which really followed the 1999 İzmit or Kocaeli earthquake. So in the 2019 code, at least, there's 4 main design levels. And you can see them there. They vary from 2% in 50 years, which is the 2475 event where we typically design for. 10% in 50 years, so 1 in 475 event, is their standard design level for their buildings. And then a few other serviceability targets. I think the one thing that's important to note is for their buildings in particular, their design target is actually the 475, and that design target and performance-based design is really going for controlled damage. So that kind of means that it's repairable after an event like this. With such extensive seismicity, Turkey has an immense strong motion and instrumented system throughout the country. And for these events, there was over 250 stations that picked them up and over about 100 that picked both events up in closer than 100 kilometers. Unfortunately, these are all surface monitoring stations. There isn't any downhole stations, but the VS-30s are typically known from either geophysical measurements or sometimes there's drilling at the site. In terms of the displacements in terms of the stations that measure these events throughout the region, you can see that quite a few, especially in that first event, measured seismic PGAs of over 0.3 G, with values all the way up to 1.4 G. The second event, which is that magnitude 7.5 Elbistan earthquake in the north, there's a little bit of an absence of stations, and that's largely because there's less cities as well as development in that area. So taking a look at one of the stations, which is on the East Anatolian Fault, you can see that the ground motions were actually quite high. The station is about 4 kilometers from the rupture. It's within our site class C, 523 meters per second. And they were seeing ground accelerations of about 1.1 G in the horizontal as well as 1 G vertical, which is quite extreme. And those effects extended pretty much the entire way down the East Anatolia Fault, and particularly in the south, with the Hatay region again seeing quite extensive ground motion amplification, again with sort of a 1.2 G in the horizontal and 1.1 G up down. And that was pretty typical of those stations in Hatay, which ranged from about 0.3 G to 1.4 G. So this all started from the surface rupture, and as Thava mentioned, as well as Marty, the surface rupture from these events was extensive. You can see I've tried to highlight where that movement has happened, and so this photo on the left is actually on the northern fault system, which was the Pseudo-Kardec, which we had about a 5.5 meter offset that bisected a hill. The offsets were typically a bit larger on the Pseudo-Kardec as opposed to the East Anatolian Fault, with offsets measuring from about 5 meters up to 7.8 on the northern fault system and 1.5 to about 4.2 meters on the East Anatolian Fault system. And one thing that was really impressive to see for myself was outside of sort of restraining bends and releasing bends into topography, the fault system, you could trace it with your eye for kilometers in the distance. And that was something I really wasn't expecting to see. Whenever those fault systems interacted with infrastructure, the offsets unfortunately caused quite a bit of damage. In instances where they went through pipelines, the pipelines ruptured, and when they went through more man-made infrastructure like this canal, they had the offset. Similarly, when they went through roads or retaining structures, we also saw large offsets in the order of about 3 to about 5 meters. Looking at retaining structures, this was one of the things that performed really well. Throughout the country, most of the retaining structures were typically unreinforced masonry gravity walls with sort of little design inferred. There was some damage, but typically that was limited to those gravity walls that were unreinforced. The MSU walls, as well as the anchor walls along the highway, we didn't see any evidence of damage. There was a few instances of things striking the walls, and that was one of the things that we saw a lot throughout the region, especially on road cuts, and was a lot of rockfall. There was a lot of mass wasting in this event. I just wanted to highlight a couple very large mobility rockfalls that we saw. You can see in these 3 photos the path of the one boulder, which is actually the boulder that's on the right, and on my tape measure I think I had about 3 meters off, so that boulder is in the order of 150 meters cubed, and its run-out length was in the order of about 300 meters, getting close to it at least. In terms of the bridges, as Thava mentioned, there was over 1,000 bridges in the 11 affected provinces, and really only a few were heavily damaged and 3 collapsed. So this is one of the instances where we had a collapse. It was the Bullum 2 bridge in Adiyaman. It's a 3-span bridge, and the easternmost span failed due to a large rockfall, where we had a rockfall that was in the order of about 50 meters cubed. It fell down the hill about 100 meters on a 50 to 60 degree slope, hit the span, and this was very quickly repaired to allow traffic to pass through. So you can see on the right, the abutment's just been infilled with essentially riprap material, and so now the one pier is now the new abutment. One of the other bridges that also failed was this bridge, the Orontes River Bridge in Hatay, which failed due to liquefaction-induced foundation failure. So at this site, the abutments were made up of 14 piles. It appeared to be more or less a rigid body rotation, where the pile abutment had rotated in about 23 degrees. And due to that liquefaction and the lateral spreading, the approach spans were lost. Again, they had already enabled traffic to flow through by refilling it in prior to when we were on site. So there was a pair of bridges, so one of them was allowing passage. The other bridge, on the other hand, was still damaged. You can see there's myself and Marty in the approach slab, and that bridge, unfortunately, due to the liquefaction that occurred, one of the hammerhead piers had actually rotated, and so they didn't allow traffic on that. Some other impacts on bridge foundations were due to seismic slope instability. So this is a morass underpass. The bridge itself was in very good shape, but unfortunately, because of the seismic slope instability, the bridge can no longer perform its function. We didn't find any evidence of liquefaction at this site, try as we did wandering around the field below, and there wasn't significant damage to the bridge structure, but due to that sort of instability, the approach embankments were lost. Continuing on that trend of seismic slope instability, a site that was rather interesting was this hydroelectric facility where, due to the ground motions that was experienced, the forebay structure had actually experienced quite large displacements, and you could see curvilinear cracks extending outwards from the forebay. And then the entire site had actually slid down approximately 5 meters, judged from satellite imagery, which resulted in the penstock buckling at one of the thrust blocks downslope. The powerhouse at the bottom was actually completely destroyed, and it was very close to the fault. And this is just an image of the before and after, as well as that kind of that overlay where you can see just how large that displacement was on the hillside. Looking at landslides, as Thava mentioned, we did have some locals show us to this landslide, and this one's been extensively reported, which was in Tafan, Hatay. And this was a very extensive landslide, which from crest to toe was about 500 meters with about 200 meters of width. The headscarp was in the order of 20 meters, and one of the things that made this slide particularly interesting while we were on site is it appears to have slid on bedding planes that were about 7 to 10 degrees and sort of a residual claystone and marl. And the overall slope as well for the entire slide mass was in the order of 10 to 20 degrees. Focusing on earth dams, again, there's over 100 dams in the region, none breached. Damage really occurred only to about 20 or so. This was the most dramatic dam that experienced displacements. So this is the Sultan Sayu Dam. It's a 60-meter high zoned earth dam built in about 1992 for irrigation purposes. There was evidence of liquefaction at the toe. The PGAs were estimated between 0.2 G for the 7.8 event and 0.36 G for the magnitude 7.5 event or 7.7, depending on which body you actually take the magnitude from. And another thing that's really important is there was no significant damage to the spillway. So while we were there, it was operating at a lower level. But there was extensive damage along the crest. We had over 400 meters of tension crack system with offsets in the order of about 2.5 meters in the horizontal and 3.5 meters in the vertical. And so you can see on the crest where, I believe that's Marty's photo of myself in there, you can see the core of the dam. As well as on the upstream face, you can see back tilted scarps. The Boyak Karagai Dam in Hatay was a dam that experienced very strong shaking, but rather insignificant damage. It was the first dam we visited. We saw this tension crack system in the order of 70 meters, and we thought, wow, this is no damage. Unfortunately, when you compare the two, you can see that this actually is very little damage. So it was a concrete rock-fill face dam. It was finished since construction and commissioned in 2019, and with the PGAs estimated between about 0.3 G in the magnitude 7.8 event, and in that one aftershock that occurred afterwards, about 0.46 G. So even with this extreme shaking, the dam itself performed very well. There was no loss in containment. The spillway structures didn't show any evidence of damage, and they appeared to be operating while we were there. Looking at waterfronts, there was extensive lateral spreading, particularly in young soils as well as reclaimed land areas. So this is one instance where we're looking at the north bank of Lake Gobusho. So you can see that there's liquefaction, lateral spreading, and that caused this seawall area to experience quite extensive damage. Another area was the D850 Malatya-Kahramanmaraş Road, where, again, lateral spreading ended up causing the roadway to be more or less fully destroyed, but they had since repaved it to allow traffic to flow. Looking at the ports, the liquefaction ended up causing quite large settlements, and then one of the things that happened as the event, which does in many earthquakes, is there was extensive fires afterwards, which made it so that that port can no longer function. The CAEEE district in Iskenderun, this is one of the areas where it was reclaimed land in the waterfront, and so there was quite extensive surface manifestations of liquefaction, as well as liquefaction-induced elements. And as a result of that, the first two city blocks in this reclaimed land area, there was widespread flooding. When we got there, we were not sure if this was a surface water problem or if it was something else, if there was just ponding. But as the tides came up, we were actually able to witness water flowing into the city. So some of the structures which were on piles, they performed quite well. They appeared to be floating. So this set of stairs was offset off the ground by about 40 centimeters. Structures that were on more spread footings, unfortunately, they ended up punching into the ground. And so this building settled about 70 centimeters. The town of Gobusha experienced extensive damage, particularly to buildings that were on shallow foundations. Primary cause of this was liquefaction and loss of bearing capacity, which resulted in punching style failure. In a lot of these areas, if there was deep foundations, they did perform quite a bit better. One of the things that's interesting to note in this is due to the liquefaction, if you actually look at these buildings structurally, they performed quite well. These structures, you can see the windows are still all in place. But unfortunately, as a result of the geotech not performing as well, they can no longer fulfill their function. So here's just a few more examples of some of those surface manifestations of liquefaction, particularly in the area of Gobusha. And we saw extensive ejecta, sand boils around the buildings, and as a result, there was uniform as well as differential settlements. Some of the uniform settlements were in the order of an entire story, whereas others were sort of in that half-story range. So structures that were, when properly engineered, they performed really well, particularly in areas where buildings quite close to them, unfortunately, didn't perform so well. Again, going back to the CAEE district in Iskandran, the Civican apartment building, it had ground improvement. From what I understand, it included diaphragm walls, and that's the building on the left. That looks like it can still maintain its function post this event. Similarly, the Iskandran Mosque, again, it appeared to be floating. It's in the air, but structurally, that building actually looks like it could still fulfill its purpose. So looking at some of the things that we've seen in terms of an observational summary, the site effects dramatically changed the results. This earthquake had extensive surface rupture, which resulted in damage to roadways, railways, and various infrastructure. The ground motions were significant. The damage to the buildings was definitely much larger than that of other infrastructure, but there was damage to bridges and as well as the hydraulic structures from both liquefaction as well as slope instabilities, landslides, and rockfalls. There was widespread liquefaction throughout areas with young sediments as well as reclaimed land. And that resulted in both lateral spreads, settlements, as well as flow slides. And deep foundations and MSE walls, they also performed really well. So let's take a step back, because often it's really easy for us to say, well, that happened over there, and it's not going to happen here. Let's take a look at some of the parallels with Southwestern BC. So both Turkey as well as Southwestern BC, they're both very complex seismic environments with potentials for large earthquakes. Especially locally, we have deep sediments, and there is that potential for ground motion amplification as well as liquefaction. And in both areas, we have existing and aging buildings and the infrastructure that's been developed on progressing codes. Where some of the differences are, though, is Türkiye, it has a higher seismicity overall, with on-land shallow strike-slip faults dominating much of their hazard. In BC, we don't know of any 300-kilometer-long faults on land. Here, with this audience, I probably don't have to mention this, but we have, three main seismic sources. We have shallow crustal, deep in slab, and subduction interface earthquakes that can result in up to M9 hazards off the coast of Vancouver Island. BC also has a much lower population density near known active faults. But one of the things that's also interesting to know is our building stock is quite different. So in BC, a lot of it's wood frame. Over there, Turkey is a concrete country. They have a lot of limestone. Our lateral systems for our buildings are also quite different. We don't have a lot of movement frame buildings here. Most of them are using a coupled shear wall system. And ultimately, one of the things is, we do have a more comprehensive review requirements for QC for both our design as well as our construction. Some of the lessons learned, understanding of seismicity is continually improving. As knowledge and code changes, risks really tend to concentrate on older structures. Aftershocks may have significant events. Here we saw how many large aftershocks there was after these events. And so sometimes these will have to be considered for performance-based designs moving forward. A big thing, I think, is adding robustness or resiliency when we can. We have to consider the reliability, the reconstruction, recovery, and collapse prevention, and ultimately life safety. And really, in order to have these acceptable outcomes, we need to have good design as well as good quality control. So a few parting thoughts while I'm up here on the soapbox. With our review, mistakes can and still do happen. It's really easy for us to say here that we're that much different, but in the end, how many times have we caught an error when we've done our independent review? Things will fail when the boundary conditions change. So regional events will really test our systems over a large area. And so when I say boundary conditions, those may be everything from a large seismic event, floods, rainfall, and to a certain set time and corrosion. And one of the last things is, are we educating the public and the owners of the limitations of our design and really what the code is doing? Our code, it's life safety, collapse prevention. The building that we see here and some of the others that we've also looked at, those all have fulfilled their life safety. But is it usable afterwards? And that can be said for a lot of various structures. I'd like to acknowledge, the people of Türkiye for their hospitality and resilience. We couldn't get out of the car without someone inviting us into their tent, and it was truly humbling to be invited into tea, and also very difficult to have to say no because we have to keep moving on. The Canadian Association of Earthquake Engineering, which is now renamed as the Canadian Association of Earthquake Engineering and Seismology. If you aren't a member, I would really consider joining it. I was incredibly fortunate to be asked to be a part of this trip. Our reconnaissance teammates. I can't stress this enough when you spend up to 16-hour days in